So this is my lab, one of two.
Yeah, and
This is my lab.
oh, this is your lab.
This is
Okay.
my instructional lab. Okay, and it's actually going to be moved, and then if we have time, I'll walk you through where the new one is. It's growing. They're making a bigger space. So ever since I started teaching, when I first taught and I teach two classes in here, one each semester. One the undergraduate level, which is a senior level elective class, and then so that's in the spring. That's what's going on now. And then in the fall, I teach a graduate course. That's also in here, at a graduate level. And from the start, when I first started, there was only 20 students. This semester, I have 60.
Ooh.
Yeah, and you can 60 people.
So
can
it's
fit in
growing
here.
quite
It's
rapidly.
growing. It's growing quite a bit. Yeah. So so now we're expanding, and then I'll show you. I'll show you the other part of the lab. How you get
Which
in
is
there.
which you have a big
Which is across the hall, which is in a building that was built in 1840s. So it's much older. Oh yeah, and I love that building. I love that building more than this one.
Oh really?
I have a thing with history, so I like old stuff.
Oh, I
Because my
see.
parents
Oh,
are-
that's
I don't
good.
throw anything away, so I keep all the old stuff. So I like it. I don't want them to throw that building or that lab away. And then you'll see. It's really, really
And
nice.
you will get it that room.
The lab, the hallway
Yeah.
that's in the front, yeah, that's
Okay.
right. Yeah.
And then, so what usually you or the students do here?
Okay, so what's interesting here is there's one caveat that I fight, that I teach in here, is because I would say 60, almost 60% of the students that initially sign up for my class probably take it out of curiosity sake, because most of them went to mechanical engineering because they don't want to learn programming. I mean, they'll literally say that. They said, Then the middle class, they go, oh my God, this is a programming class. You know, and they said, I went into mechanical engineering because I didn't want to learn programming. Okay, that's the intent. This is what I teach. I teach essentially programming for mechanical engineers. Because now software is a vital tool for mechanical engineers, no longer screwdrivers and crescent wrench. Okay, it is clearly, that's it. I mean, look at a car, right? A car which was traditionally mechanical, purely all mechanical, carburetor and everything before, forget it now.
gone.
There's
Yeah.
more than 5 computers that are on there. Fuel injection is done, by computers. Everything else, the plane that you're flying in, has a computer in it. Okay,
So
these are all traditional mechanical systems. Your microwave has a computer in it, for heaven's sakes. So, so this is what I sort of teach here. Okay, each of these stations actually have 2 computers. We don't, Windows is just a media for them to do the development, but they actually run on a computer that's supposed to be embedded. Okay, so it doesn't really have an OS. Okay, and that's what they do, and they control mechanisms. Right, so what they learn here is to design programs, right, that will actually interact with sensors, interact with actuators, having to deal with mechanical systems. The courses that are here and the concepts here is a little bit more difficult than actually computer science, believe it or not. Not necessarily in the sense of algorithm development, but traditionally in computer science, if you talk to them, okay, if you look at what the curriculum for computer science is, or what the belief in computer science is, that it maps one mathematical function to another. Okay? And all the function of the computer does, and all that science behind it, is that it does that accurately and correctly every time and the same. That's all their caveat is. Once you've defined it, it will map one mathematical space to another. Okay?
Right,
And then that's it. And then the idea is to develop that algorithm in between. The interesting thing is the notion of time never enters into the picture. You can look back. You look back into computer science, time is never there. Okay? It's never there in the solution. As long as the solution is correct, it's fine. It doesn't matter when it comes. Now, of course, we want it sooner than later. Okay? A classic example for this, which they still hunt, is weather prediction. Okay? The algorithm for weather prediction can actually be done. I mean, literally, there are algorithms and models. They know enough of the weather, right? To almost to 90% they can predict the weather. Now you'll sit there and go, well, how come the weather forecasts are still wrong? The problem is they need the data all the way up to the minute that the next minute weather pattern is going to be. the next hour. They need it up to then, and it's fine. If the computer can solve it in 30 seconds, you'll have a 30-second warning of what the next weather is going to be like the next minute. The problem is, right now, even with today's current technology, it takes 3 days to solve all that problem. You have so much data to process, and 3 days later, the answer comes out. They look back in history and they go, hey, we're dead on. Okay, but the problem is still, that's why there's still a forecast. There's 5-day forecast. So they do the best that they can. They run all the other scenarios, right? And they sit there and they go, okay. You know, there are many scenarios they can predict, but it's not quite accurate. So they sort of, okay, pick the best that they can, and they, then later, 3 days later, they'll sit there and go, they'll confirm all of this. Okay?
So do they put time in the equation?
In the algorithm, there is no time into it, right? Because the answer comes 3 days later. So technically people would say, well, that's sort of useless.
Yes.
Right? But the computer science belief is sit there and go, why are you worried about time? Right? 6 years from now, our computer's going to be 10 times faster. So far, they're correct. Right? So between mechanical engineering and electrical engineering, we are sitting here serving computer science in terms of technology to fill out Moore's law. Right? Right? So far, yes. If you look at history, they're absolutely right. Every 6 months, the computer speed is pretty much doubling now. Okay?
That's correct.
They thought they thought they've hit the wall, but again, no, it keeps going. Okay? So the problem is time never enters it. You go over there and you ask them with the time of the problem, they'll sit there now, what's the big deal? 6 months from now, you don't have to worry, right? The answer is going to be fast enough. Well, here, it is not the case. Time is very important, okay? Because what happens is we are hooked up with a mechanical system, right? There, it doesn't matter, okay? The weather comes out 3 days later. Yeah, what's the big deal? The weather's going to move its own course, right? You don't care. Your pride might be wrong if you predicted it wrong.
Right.
But the answer still comes out. As long as the algorithm is correct and the answer correct, they don't care, okay? Same thing when you're typing on a Word text, right? Windows decides to go away for some odd reason. Yeah, you might get frustrated and you type a few keys, and then the keys will come out later, and then you go backspace and erase it. No big deal, right? No one dies, the world doesn't explode, nothing else happens, right? Or you're sitting there, and you've seen this, right? You've served around the internet, and all of a sudden the internet gets stuck. And you wait there, you might curse a little bit and get a little bit upset. But it comes back and it's okay. Time is not important. Here, imagine if you had Windows controlling a 747 that's flying at 300 miles an hour in the air. Right? All of a sudden, Windows decides to go away for 3 seconds. Well, at 300 miles an hour, okay, you're going to miss your target. Right? And so it's important. So the other aspect is that these mechanical systems like robots and so forth, and that's why we use robots, because robots are great examples of these. If you don't answer it, right, the robot's going to keep moving. The robot does not know. So the computer has to come out. If you design the system to be stable, where you sit there and say, okay, every second I need the answer, and this is how it is. And the whole system and the discipline comes in with the mechanical system, where you design, you know what the limitation of the mechanical system is going to be with the 1 second answer. That answer has to be there on the second, on the dot. Okay? So the funny thing is, then people that don't necessarily understand this discipline, you go to computer science and you describe this. What are you
They don't
worried?
have a clue.
It's not that they don't have a clue. They'll sit there and go, what are you worried about? Okay? So this is the other side and the caveat of the discipline. It's at 1 second, right? Computer science, why are you worried about it? In 6 months, you're going to have a computer that can do it in half a second. Ha ha ha! That's the problem. It is not only speed. If we designed it to come in a second, 6 months from now, if there's a computer that comes in and it starts doing it in half a second, you cannot apply the 1 second theory in half a second, even though it's faster. It doesn't work. Okay?
Makes sense,
If it's a second, it's got to be a second. Okay? So these are the things that we sort of struggle with, because as computer speeds up, if you are designing a system with slower sampling time, or what are these called, legacy type products, the newer computers run havoc with them because we can't get them to go slow enough for some of the system. This is not necessarily true. Then you redesign the system. It's always better to go faster and faster. Not always, but in most cases it is. And this is sort of what we teach the mechanical engineers here.